What is enthalpy? Enthalpy is a measure of heat flow at constant pressure. The symbol for enthalpy is a capital H. So is it a state function? Yes, it is, and we know that because it's a capital letter. So since it's a state function, that means we don't have to actually know the amount of enthalpy something has. We can measure a change in enthalpy. So that's what you're looking at most of the time, is a change in enthalpy. And it says that enthalpy is a measure of heat. What's the symbol for heat? Q. So enthalpy is actually Q. And usually we put a little P on the Q to note that we're talking about heat at constant pressure. Well, what does that mean, constant pressure? Well, anytime you carry out an experiment in the lab, if you don't have a lid on your beaker or Erlenmeyer flask, you're at constant pressure. Because do y'all know what pressure we're at in terms of atmospheres? We're at 1 atmosphere. We're actually at 1 atmosphere. So you're carrying out the experiment at constant pressure. Because, you know, when whatever happens, if a gas is given off, it has to do work. We've talked about work, but how is it doing work? Well, when something in a beaker produces a gas, it's got to push atmosphere out of the way for that gas to evolve, because gases expand, right, to fill the volume of their container. You could actually visualize the work being done if you took something like a balloon that's deflated and you put it on the top of a test tube and you allowed things to mix in there. If it gave off a gas, what would the balloon do? The balloon would inflate, wouldn't it? And so you can then see the work being done, but it's still at constant pressure. Now, what if you mix these chemicals and you allow them to generate heat, give off a gas, whatever, but you've got a lid on your container? It's probably going to blow up, right? Because why? What's happening? Why is it going to blow up?
It's not big enough for the pressure, and it's going to flame.
Exactly. If it gives off enough of a gas or enough heat, the pressure is going to increase and it would blow up. That's what the Drano bomb experiment that we did, right? Well, we didn't do it. We did it at constant pressure. We did it open, but if you ever play with that very carefully on your own, you put the lid on the Coke bottle and it explodes because of pressure. Since enthalpy is a measure of heat, we can use the sign of enthalpy to know if it's endothermic or exothermic. And it's going to be the same thing as how it applied to heat. If you have a negative enthalpy, then that would mean exothermic. And a positive delta H would mean endothermic. And units for enthalpy are the same units we've been talking about. It's going to be joules or kilojoules. That's how enthalpy will be reported. For this process, water or ice melting, I'm looking at the number in the book, so I know that the delta H for this process is 6.01 kilojoules per mole. When you have a balanced equation like that with the delta H written after it, that is called a thermochemical equation. What does that mean? That means that when 1 mole of ice melts, it requires 6.01 kilojoules of heat to melt 1 mole of ice. How much heat do you think would be required to melt 2 moles of ice? 12.02. Okay? So do you see that this delta H can be related to the coefficients of this equation, however it works out? So 1 mole of ice, 1 mole of H2O, how many grams is that? 18 18.02. What is that? Where are you getting that number? Right, the molar mass, the AMU, from the periodic table. So I know that 18.02 grams of ice would require 6.01 kilojoules of heat. So how much heat is required to melt 147 grams of H2O? First thing we should do is convert grams to moles, because we said if you don't know what to do, convert grams to moles every time, right? So convert grams to moles. And that's dividing it by the 18.02 grams of water. Our balanced thermochemical equation gives us a way to relate the amount of heat required or produced, depending on whether it's positive or negative, to the moles of a certain component of a reaction. And so for this one, as we were discussing earlier, 1 mole of water needs 6.01 kilojoules of heat. So can't we set that up here in this ratio? We know from that balanced equation that 1 mole of H2O takes 6.01 kilojoules of heat. Now, why did we use 1 mole of H2O on the bottom? Because that's the coefficient in the equation. Had the coefficient up there been 2, we would have to use the coefficient here. It's like what you did last chapter, last test on stoichiometry. This last relationship, we get those numbers from the balanced chemical equation. And so what's our answer going to be? 49.03? Punched it in quicker than I did. Yeah. So I'm just going to say 49.0 kilojoules. Okay, so that's our balanced thermochemical equation for the combustion of methane. Let's calculate the amount of heat released when 1.4 times 10 to the 3 grams of oxygen is reacted. And of course, it's according to that equation that we just wrote. Okay. So the first step is to convert grams to moles. Why? Because the balanced equation, I know that 2 moles of oxygen will release 802.4 kilojoules of heat. So in my last conversion, I'm going to use that 802.4 kilojoules. And this time I've got to put it over 2 moles of oxygen because the coefficient of oxygen is 2. And I'll get 1.8 times 10 to the 4. The negative is not necessary. The negative is just telling us it's released. You can use the negative. But the question says calculate the amount of heat released. Okay, so realize the negative is, again, it's just telling direction. Let's calculate the mass of methane needed to generate 48.2 kilojoules of heat according to that same equation. With,
AMU of methane?
well, I got to start with what I'm given in the problem. I need to start with the 48.2 kilojoules of heat. Now, using the equation, I can get from kilojoules of heat, right? Put it on the bottom so that it'll cancel, to moles of anything up there. But for this one, I've got to go to moles of CH4, don't I?
8. It'd be 1 over 802.4.
Yes, it's going to be 1 over 802.4. And so at this point, kilojoules will cancel. The question's asking me for grams. So now I've got to get moles to cancel and convert that to grams. And it's moles of CH4 to grams of CH4. And the molar mass of CH4, I think, is 16.05. And I get 0.964 grams of CH4.